In this video, I'm going to do a hypothesis test for a population mean when sigma is known. A newspaper article noted that the mean lifespan for 35 male symphony conductors was 73.4 years, in contrast to the mean of 69.5 years for males in the general population. Assuming the population standard deviation of the lifespan of male symphony conductors is 8.7 years, use a level of significance of 0.05 to test the claim that male symphony conductors have a mean lifespan that is greater than 69.5 years. Now this is going to be a hypothesis test for the mean when sigma is known, and the conditions are met to use a z-test. Because the sample size is more than 30 and the standard deviation is known, we can go ahead and use the standardized test statistic that follows the z-distribution. If our sample size was less than 30, we would need to be told that the population was normally distributed. If sigma was unknown, we would need to be told that the population, if sigma is unknown, we would need to use the sample standard deviation and be told that the population distribution is normal, and then the conditions would be met to use a t-test. Okay, that was a mouthful. So to summarize what's given, we're given our sample size of 35, sigma, the population standard deviation, is 8.7, and the sample mean from that 35 was 73.4. The claim needs to be written in terms of a mathematical statement using the population parameter mu, and the claim is that the lifespan is greater than 69.5. So that makes the claim mu greater than 69.5. That does not contain the case of equality, so that makes the claim the alternative hypothesis. So the alternative hypothesis is that mu is 69.5, and the null hypothesis contains the case of equality. Some textbooks use the complete opposite case. If we have greater than in the alternative, some textbooks or websites use less than or equal to in the null, and others use the strict case of equality. In either case, the case of equality always belongs in the null. Our standardized test statistic is a z-score. It's what we observe, the sample mean, minus the hypothesized mean, over sigma over the square root of n. Plugging in that information from what's given in the problem, and I suggest using parentheses around the numerator expression and the denominator expression when inputting into your calculator. The test statistic in standardized form is 2.652. Interpreting this as a z-score, which it is, this means that what we observe is 2.652 standard deviations away from the mean. So this is an unusual observation using the criteria of it being more than 2 standard deviations away from the mean. But I'm going to use the critical value method first. To find the critical value, you need to use the level of significance, alpha, which is 0.05. That is an area. And sketching the standard normal distribution, shading the area of rejection and indicating that area of rejection is 0.05. I'm shading the area of rejection on the right because this is an upper tail test or right tail test. Using the inverse normal function on the TI-84, which I've done in a previous video, several previous videos. The critical value is 1.645. To use your inverse normal function on the calculator, it expects a cumulative area as its input. The cumulative area to the left of that critical value is 0.95. So if you have an older TI-84, where you can't change the tail direction, you're going to have to input an area of 0.95 to get this critical value. So 2.652, the standardized test statistic, is definitely greater than 1.645. So I know my decision is to reject the null hypothesis. When we reject the null hypothesis, we can conclude that there is sufficient evidence to claim that male symphony conductors have a mean lifespan that is greater than 69.5 years. Now, to use the p-value method, you have to find the area further to the right of that standardized test statistic. So the p-value is the probability of getting a test statistic at least as extreme as the one obtained by the sample, assuming the null hypothesis is true. So when you're given a z-score and you're trying to find an area, in probability notation, that would be the probability z greater than 2.652. You would use your normal CDF in the TI-84. You could input, or you would input 2.652 as your lower bound and a very large number as your upper bound, leaving mu and sigma as 0 and 1 respectively. And then your calculator would output 0.004. 0.004 is clearly less than 0.05. If your p-value is less than your level of significance, then your decision will be to reject the null. You will get the same decision whether you use the critical value method or the p-value method. Because the null is rejected, it is possible that a type 1 error occurred. It doesn't mean that it did, but in terms of is this a type 1 error or a type 2 error as our possible errors, this would be a type 1 error. Now, to get the standardized test statistic and p-value all in one step in the calculator, press your stat button, and this is on the TI-84, arrow over to tests. The first option is z-test, and in this problem we have the summary statistics, not the data in a column. You input the null statement of 69.5 and then our assumed standard deviation, population standard deviation of 8.7. The sample mean was 73.4, sample size was 35, and then you can change your direction of alternative if you need to for the problem. This is an upper tail test, so I want to leave that as is. Okay, I had previously entered this before. Enter it, calculate, and you'll see that the standardized test statistic is the same that I got by hand, rounded to 3 decimal places, and the corresponding p-value is also the same.